Hello and welcome to the podcast. Today, we're diving into the future of energy storage, solid-state batteries. You've probably heard the buzz. They promise more energy, faster charging, longer life, and greater safety than the lithium-ion batteries powering most things today. Imagine electric cars with vastly extended range, or devices that charge in minutes. The potential is huge. But, as with any groundbreaking technology, moving from lab samples to mass-produced batteries that can power your car is a massive leap. There are some serious engineering mountains to climb. Let's break down the key hurdles. First up is manufacturing. Building solid-state batteries isn't like making current batteries. The processes are often complex and don't easily fit into existing factory lines. Scaling up lab techniques, like simple powder pressing, often doesn't work for durable, real-world batteries. New methods like hot rolling or thin film deposition look promising, but getting them to high-volume, affordable production is tough. This often means building entirely new, expensive facilities. Cost is a big factor. The special materials needed, especially the solid electrolytes, can be pricey. Combine that with complex manufacturing, and early solid-state batteries are expensive compared to mature lithium-ion tech. Finally, quality control is critical. Making perfectly thin, defect-free electrolyte layers and ensuring perfect contact with the electrodes across millions of units is incredibly demanding. Tiny variations can kill performance or even create safety risks. Next, let's talk materials. The solid nature of these batteries creates unique problems. Solid electrolytes, especially ceramics, can be brittle. That makes them hard to handle during manufacturing and prone to cracking from vibrations, say, in a moving car. Finding materials that are strong, stable, conduct ions well, and play nice with the electrodes is a major research focus. Another huge challenge is the interface, where the solid electrolyte meets the solid electrode. Unlike liquids that just flow into place, getting perfect, lasting contact between two solids is hard. Any gap increases resistance, slowing down ion movement and hurting performance. This gets worse because electrodes naturally swell and shrink during charging cycles, potentially breaking that crucial contact. While solid electrolytes are generally safer regarding dendrites, those nasty lithium spikes that can cause short circuits, the risk isn't zero, especially with high-performance lithium metal anodes. And many solid electrolytes don't conduct ions as well as liquids, particularly in the cold, limiting power and charging speed. Finally, putting these cells into a larger system, like an EV battery pack, brings its own headaches. Because everything is solid, mechanical stress travels easily. When electrodes expand, sometimes dramatically, like 300% for lithium metal, it puts immense strain on the cell. Managing this expansion, this breathing of the battery pack within a tight space like a car chassis, is a complex design puzzle. Think about needing maybe 10 centimeters of wiggle room just for the battery pack itself. Thermal management is also different. Solids might handle heat better overall, but they aren't always great at dissipating it. Keeping the battery at its optimal temperature requires smart, possibly complex cooling systems. Plus, many solid-state designs need constant external pressure to maintain that vital internal contact, adding another layer of complexity to pack and vehicle design. Optimizing the control systems, like the battery management system, is also tricky without large amounts of real-world data. And we can't forget recycling. Figuring out how to efficiently reclaim materials from these new battery chemistries is essential for sustainability. So while solid-state batteries hold incredible promise, the road to widespread use is paved with significant engineering challenges across manufacturing, materials, science, and system integration. Overcoming these requires intense innovation and investment. The race is on, and researchers worldwide are working hard to unlock the true potential of this next-generation battery technology. Thanks for tuning in.